Okay. Sorry, just started recording. I was just mentioning to everyone. We're pulling up the notes from Friday because we stopped in the middle of a problem that we want to continue. We have our parametric equations. And we were finding that there were two tangent lines at 3, 0. We found our times by setting each coordinate equal to the respective value. And then we found the 2 times positive square root of 3 and negative square root of 3 of when we are at this coordinate. So to find the tangent line is going to come from the derivatives. And what we can do is we can keep track of the individual rates of change of our coordinate parameterization. So namely, this guy here is just the derivative of our x function, so x prime of t, and this guy here is our y prime of t. We want to keep track of both of those. In higher math classes, you'll learn that it's very common to simply keep track of them in a vector, what we call a vector, and we would call this the directional vector or the velocity vector. But for now, you can really just think of it as an ordered pair. We want to keep track of our xy ordered pair and what's going on with these functions separately. So you can kind of just think of it as, well, we're keeping our x values in a list and our y function in a list. And now we're keeping track of the derivative of x and derivative of y in that list. And so what do we do? How do we find the tangent lines? So the tangent lines, we still want the rates of change, right? We still need dy dx, the slope. And how do we get that? We're going to get that from the chain rule. So dy dx is going to be dy dt times dt dx. And we want to think of dt dx as simply one over dx dt. And I mean, it is a little weird. I've tried to mention in this class before of how we like to consider our fourth order differentials. They really do behave in many ways like fractions. So the other way we could arrive at this same equation is if you actually started from dy dt and used the chain rule. And now we would divide both sides by the quantity dx dt and arrive at the same formula. So really all we want to do is to take the quotient of our respective derivatives. I think I was mentioning this on Friday. I don't think we ever got to see it. We're starting to see it now. But it should be fairly intuitive that if I have a rate of change of my x coordinate and a rate of change of my y coordinate, both with respect to t, to time, then how do I find the relative rates of change with respect from one coordinate to the other? In other words, find, say, dy with respect to dt or dx. We would just take the quotient of those two. So nothing terribly difficult there, conceptual-wise. So our dy dx is going to be 3t squared minus 3 over 2t. And we have 2 times we were considering, square root of 3 and negative square root of 3. So all we got to do, plug in those times to find the slopes of the tangent lines. So dy dx evaluated at t is equal to square root of 3. It is common in some sense, like if we have dy dx, sometimes you might want to write it. Sorry, I don't have space over there. It's a little bit confusing in terms of the notation. If we have dy dx, it is almost always implied that this is the independent variable. But if we're computing things with respect to t, sometimes you might want to put in of t, our function as dy dx, the independent variable as t, just to keep track, or if that's a little confusing for you. But we're plugging in our square root of 3, so we'll have 3 times 3 minus 3 over 2 root 3. And so we are going to get 6 over 2 root 3, or square root of 3. Likewise for our other value, dy dx evaluated at t is negative square root of 3. We're going to have 3 times 3 again, minus 3 over 2 times negative square root of 3. So 6 over negative square root of 3, or 2 square root of 3, is going to give us negative square root of 3. And so our last step, how do we actually write these equations? So t equals square root of 3. Of course, we have our point. It's still going to be 3, 0 for both of these. So we've got our x and y coordinate. And then now we've got our slopes. So we can do y. We can do point slope form is the best. Of course, y minus 0 is going to be square root of 3 times x minus 3. And then our other line will have a negative slope. And so we'll get y is equal to negative root 3x plus 3 root 3. So I will leave this to you guys to graph it. And if you want a rigorous graphing calculator, I'm sure you guys can find online tools to do it. I think most people at this point in time have used Desmos. And Desmos will graph parametric equations for you, so you can use that to check your work. Of course, you want to practice graphing it yourself. And what you should find is whatever the graph does, it'll cross the point 3, 0 twice. So it'll do something. It'll probably make some loops somewhere somehow. I don't know exactly where it's going to intersect, but then it'll kind of cross and come up going in one direction. And then at the other time, it'll cross and be going downward. And you'll see the tangent lines make an X there. Any questions on this guy? Okay, so let's get into polar coordinates, though we do have one last thing to mention on parametric equations, and that's areas. This isn't, I haven't seen it come up a lot, and I was looking at your guys' problem sets. I don't think it comes up on the written homework, since areas with respect to parametric equations, it's usually It's not really done in terms of areas. Parametric equations is much better in terms of arc length and lines. Oh wait, that does remind me. Actually, we need to talk about arc length too. Arc length is going to be far more important, and parametric equations give us a very nice way of computing arc length. And so the thing you should be gathering, since we've been talking about parametric equations for the past few days, is it's really all about the curve and being able to model a much broader array of curves with this independent parameter of time. And so areas gets a little weird, but since we have these curves that move through space over time, maybe they loop back on themselves, maybe they don't. Sometimes they keep going off somewhere into infinity. We have the same problem that we need to solve in terms of arc length, namely that if I start at a given point and then we traverse the curve over time and then end at a given point, how do we find arc length? So it's actually easier with our parametrizations now. With our our rectilinear coordinates, our Cartesian coordinates, we had to kind of finagle some things around, and we came up with this formula that is it's not a very useful formula, to be honest. It's a very like introductory Calc 2 formula that only worked for a specific nice set of curves. Most of the curves we would try to actually compute if we had Cartesian coordinates for, they wouldn't work well with that formula, right? So what did we have? That the arc length was the integral of 1 plus f prime of x squared dx. And so it creates all sorts of issues. We've seen how hard it can be to integrate square roots, especially if there's a sum underneath the square root. And moreover, now if the derivative of whatever function, of whatever curve we're modeling, if dy dx isn't a nice derivative, and then I square it and add 1, it's very niche cases that will actually work underneath a square root and be able to compute by hand. But how did we get this formula? So maybe we just take a step back, and if you kind of remember that if we had this curve, so let's think this maybe just a small little piece of a curve, and we take a window and kind of blow it up and see what's going on in a small little piece of curve, then what did we do? Well, we approximated the curve with a triangle, and we called, well, the vertical component was our change in y, our dy or our delta y, and the horizontal component, of course, dx. And the actual piece of the curve on the diagonal, this was our ds. Sorry, let's use d little s. I should use a little s here. Capital S we usually mean for surface area. Little s, arc length or distance. And by the nice Pythagorean theorem, we came up with ds squared is dx squared plus dy squared. We did some finagling here. Of course, there's going to be a square root if we solve for ds. But then underneath the square root, we did some factoring of dx squareds and pulled those outside of the square root to get a dy dx or a dx dy, depending on which independent coordinate you want to choose. But now we already have our independent coordinate, our independent parameter, and that's time. So there's time hidden already within these. And typically, if we already have equations, x is going to be some function of time, and y is going to be some function of time. let's call it g of t, then just like we've done with u substitutions and trig substitutions, when we have a substitution for a variable, and this is kind of what you can think of as these parameters in some sense. If we have a Cartesian equation, and then I give you a parameterization, x is equal to something, y is equal to something, and you want to check whether or not that Cartesian equation remains valid under this system of transformations, of substitutions, then we would simply, plug in the f of t's for our x, plug in the g of t's for our y, and see if that Cartesian equation still holds. If it does, then this would be a valid parameterization. Conversely, if we have a valid parameterization, you can kind of think of it as, well, this might be something we want to substitute into a Cartesian equation, even though we may not actually be given the Cartesian equation. But with that kind of intuition and thought process, well, means we can kind of treat it just the same as we would as like a u substitution, where if I'm trying to integrate something and we have an equation or a formula for an area that we want to compute, well, we're making a substitution. And how do we compute the differentials? We take derivatives. So we would simply get that our dx is f prime of t dt, and our dy is g prime of t dt. And now we can substitute our differentials into the equation relating them. So our arc length is just going to be f prime of t dt. We would, of course, square it, and then g prime of t, square that one. Now, when we square the differentials, I can factor that out and then factor that square differential outside the square root. And so we're going to get f prime squared plus g prime squared, and then we would factor out that dt. Now, this is a little bit vague notation. I did have to set up my x and y in terms of what our parameterizations are. So more commonly, how are we going to see this formula? It's really just dy dx, or excuse me, dx dt squared plus dy dt squared. So now there's kind of no confusion as to what those f's and g's were. So, for example, let's rewrite that equation first. So our dx is square root of dx dt dy dt. Square them both, add them up, take square root, and then integrate with respect to time. Examples. Find the length of the curve defined by x is equal to e to the t plus e to the minus t, and y is equal to 5 minus 2t for t between 0 and 3. So arc length, it's all going to be formulaic, similar to the last time we did arc length. Now there's just a little bit more computations to do, but I do think in general with parameterizations, it's a bit easier in terms of a lot of the functions that we give and the way the simplification works out underneath the square root. So let's go ahead and compute our pieces here. So our dx dt is e to the t minus e to the t, negative t. And dy dt is just minus 2. I'm going to go ahead and square both before we plug them into the formula, just to save ourselves some space writing underneath that square root. So our dx dt, e to the t minus e to the minus t squared. So let's compute all that out and simplify here. We're going to have e to the 2t minus 2 times the product. That's just going to give us 1. And then plus e to the minus 2t. And then dy dt squared, going to give us 4. And so we can even add those if you want to do a lot more of the scratch work outside of the square root. Sometimes it's easier to just organize while you have the space to write it all. If we want to write out our dy dx, or sorry, our dx dt squared plus dy dt squared is going to be equal e to the 2t minus 2 plus e to the minus 2t, and then plus 4. So simplifies quite nicely, e to the 2t plus 2 plus e to the minus 2t. And so now when we want to find our arc length, nicely enough, the bounds are 0 to 3. So always keep in mind that the bounds, since we are now integrating with respect to time, the bounds have to be time bounds. So be careful if they give you points. If they say find the length of the curve between two given points and they give you x, y coordinates, you need to find the times coordinating to those coordinates. Okay, and so we want square root of e to the 2t plus 2 plus e to the minus 2t dt. So of course, arc length, I guess I could have wrote out the step that s is the integral of ds, right, our generic first step. And since we have our formula for the differential, we would simply put that underneath the integral. And then now the step with a lot of these, since we are integrating a square root, you got to look, well, what's under the square root? If it seems rather exotic and rather a complicated function, you should look to see for some sort of perfect square. And you should kind of recognize the fact that our dx dt, we had an e to the t minus e to the minus t. And when we square this out, we get something with a negative 2 here. Now we have that same expression, except with just a positive 2. So you can maybe try to reverse engineer the factoring techniques. And so this is going to be e to the 2t, or e to the t, excuse me, plus e to the minus t. That whole quantity squared underneath our square root. And now these square root and squaring operations will undo each other. And so we will just be left with integrating e to the t plus e to the minus t dt. And then let's see, I think we'll have enough space here to write it. That's just going to be e to the t minus e to the minus t again. And then 0 to 3, evaluating e to the 3 minus e to the minus 3 minus 1 minus 1. So we just get e to the 3 minus e to the minus 3. Any questions on that? Okay, a couple notes. So a few things that are left in terms of the calculus of parametric curves, areas, and actually we want to talk about the second derivatives real quick. Neither of those are too difficult. It's just some more calculations. So areas, I think I was saying a little bit earlier, areas you don't do a whole lot with parametric curves. Sounds like they were on the WebAssign now. So let's just kind of touch base on that. So areas in terms of parametrics, it's a little weird because the reason we're using parametric curves is to describe a more complex curve. And when we actually want to find areas, it's so far we've only really found areas with respect to dx or dy, and we really need these rectilinear and Cartesian coordinates. To do areas properly for really complex shapes that might be defined by a parametric curve, you really want Calc 3 techniques, and you'll get into what are called double integrals. But I mean, for the sake of understanding calculus, we can do it in terms of parametrics, right? Typically, our area is going to be the integral of f of x dx, or conversely, the area is going to be something like g of y dy. Whereas in this case, we are finding the area underneath some curve f of x. And this comes from our Riemann sums. Whoop, drew that bar too big. Where the height of each bar is going to be the height of f of x, and then the width of each bar is dx. Conversely, if we do it with respect to y, it just means we're going to have our bars going horizontal. And now the width of each bar is dy, and the length is going to be g of y. So we can essentially do the same things if we have parametrizations. Then we're simply going to take either of those formulas, except instead of now f of x dx, really another way to write that is just y dx. Right? We're taking the y coordinate as the height, and our width is dx. If we have parametrizations of y is equal to, let's keep our same values. We were using x is equal to f of t, and y is equal to g of t. Well, we just make those substitutions. And so it's going to be the integral of f of, g of t. And then our dx is f prime of t dt. In other words, we're going to have the integral of y times dx dt dt. Likewise, for if we were doing it the other way, if we had our area as x dy, and now we want to think of it as our x, we can write as f of t, or sometimes we write it simply as x is x of t, and then our dy is dy dt dt. So think of it just like making a u substitution again. The differential, mind the differential. Here we're integrating with respect to x, but if I don't have y as a function of x, instead I have y as a function of t, I can substitute in the function we have in terms of t for y, and then substitute in the differential in terms we have for t in terms of x, or substitute the differential we have for x in terms of t. Second derivatives are one thing to note. It's just kind of hairy. If you want to find the concavity, it gets into a little bit messy of a formula if you really want a proper formula in terms of t. So our second derivative of y is just another derivative of dy dx. And for dy dx, remember we had this formula, or this chain rule formula, that if we have, let's make a substitution just so we can write it out, because it's going to follow the same way we derived the formula for the derivative dy dx. How did we derive that in terms of our differentials in terms of t? Well, it was just the chain rule. So of course, if we called that u, d dx of u is going to be du dt times dt du, which we also described as du dt over, wait a minute, dt dx, excuse me, missed one of those, over dx dt. And so really what our second derivative formula is going to be is, if our u is dy dx, we now want to essentially substitute our formula for dy dx in there. But what was our dy dx? Was dy dt over dx dt. So the formula is going to get a little complicated. If we plugged in this whole formula for dy dx into u here, and then took another time derivative of this, we then have to use the quotient rule. And you can do that, but you've got a quotient rule of derivatives, of first derivatives, and then you'd have the quotient after that of dx dt. And you can do that. You can come up with a formula for the second derivatives. I would encourage you to do that if you're curious. However, it's a little complicated, more complicated than necessary, because really what this formula is saying it's giving us the algorithm for doing it in pieces if we leave it like this. So our first step would be to compute dy dx as a function of time. So I'll put that independent variable in there. So essentially use this formula here, and you will get a function of time. Simplify that function of time. So exactly like we did in our last example, we had to compute the slopes and compute these dy dx's. And so we were going to have these two functions, dy dt and dx dt, take their quotient, do the algebraic simplification, and now we just have a regular function of time, which you can compute another derivative of. So it's easiest to do that step first, and then realize, well, if I just compute another time derivative of it, and then divide by another copy of dx dt, then that gives us the formula for the concavity, the second derivative of y with respect to x. So take another time derivative. And then divide by another copy of dx dt. That way might be a little more quicker and easier to kind of at least think through the algorithm, rather than if we extended this from here and substituted this quotient in for here and then took a time derivative, you could come up with just a rigorous formula in terms of second derivatives of x, second and first derivatives of both x and y with respect to time, that would simplify to a second derivative of y with respect to x. But it gets a little messy. So let me know if you guys want to see that. Happy to help you work that out in the office hours. But honestly, I think this way is a little bit easier. And I think that's the way the book does it as well. Okay, any questions on those guys? Okay, so we had a question. Arc length and area was on WebAssign last night. Let me take a look. Yeah, we're lagging a little bit behind, which isn't bad, just half a day. I did want to properly introduce parametric curves. And it took us a little bit longer last week. We didn't have as much time to get into this calculus.
Can I ask you a question?
Yeah, go ahead.
It's not exactly about, it's about calc, but like you said, we're a day behind. I'm gonna be honest, I wasn't here on Friday for class just because I had to go down. I'm driving down to a vacation with my fam. I was doing that on Friday. I did the WebAssigns. I thought this would have been taught on the WebAssign, but I'm talking to people in this class, and like some people got like 30% because this wasn't taught before we did the WebAssign.
Yeah.
Is there a possibility they could extend it?
That's what I'm looking at now. That's
if we're behind, yeah.
Yeah, that's what someone was asking in the chat. I didn't realize it was on. Not a full day. We're a half a day, but those are pretty key topics. And if they were on last night's WebAssign, I will try to extend it for you guys. I'll just need to clear it with OCEDA. And I don't.
Well, we didn't learn polar coordinates and arc length. And that was literally the entire WebAssign last night.
Those do last. Wait, polar coordinates were on there?
Well, there was.
We're not even getting to polar coordinates today. Today is the official polar coordinates.
I guess, but like there was some stuff with it.
That's kind of weird.
I don't know, but it was mostly like arc length and stuff like that. We didn't even learn.
Yeah, find that. Find the. Yeah.
Like even like, don't worry about the when I said polar coordinates, but like even the fact that we didn't learn the stuff that was on the WebAssign last night, I feel like it's kind of messed up.
No, totally.
Just putting that out there. Thanks.
Yeah. No, you're right. I mean, it's polar, but it's not polar. It's us hinting at what polar equations are by parametrizing with respect to theta. So, yeah. No, but you're right. Find the exact length of curves and stuff like that. Yeah. And we didn't get to it on Friday. Yeah, I'll see if we can open that up again. At least give you guys till tonight to do it. I'll check with OCEDA, especially since this section is bigger than his. Since most of the students are in this section, and since we didn't get to it, it'll probably be okay, because I know OCEDA, the other section, usually when I talk to him, we're kind of, I think I've been a little bit ahead last week. And I don't know if he caught up and got ahead or where he's at. So I'll check with him. But in my opinion, I would like to open it up for you guys, especially since we are just covering that now today for you guys. So I'll send an email out later about that. Let's see. Website number 22, I think it was. And actually, is it the last one? Or is there another one? Let me see all the assignments. Let's see how many WebAssigns you guys have. Just in case we need to like shift some of the other ones. Okay, yeah. So there's 2 more WebAssigns. So there's 22, 23, and 24. And it looks like number 23 isn't due until the 21st. So you've got a couple days to even get started on that. And then the other one is due on the 22nd. So since there's kind of a day or so here, I don't think it should be a problem of opening up WebAssign number 22 again and give you guys at least another day on that. Okay. So let's get into polar coordinates. Official polar coordinates. We've kind of hinted at polar coordinates where sometimes we have curves where we've seen like these ellipses and circles where the curve itself, we don't necessarily want to think about traversing the curve in time while we can. We can also kind of think about modeling whatever points.
Excuse me. Can we go back? Can I like just ask a really quick question like before we get into this?
Yeah,
You said
sure.
there's 2 more WebAssigns for us to do.
Yeah.
We have no assignments in WebAssign.
Yeah, I know. That's kind of what I was saying. They haven't been posted yet. This has been.
So they're gonna give us 2 WebAssigns to do it the week before our final, and they haven't even assigned them yet.
No, they're assigned. It just looked like they haven't like appeared up on the
potato potato, like, but like still.
So what are you? So all of
I'm
the
just saying, like,
assignments.
I know it's not in your control, but like, can you talk to them? Because we've had a WebAssign due every night before an exam, and that's not right. This is not okay. Like, that's not cool. Like, I'm not saying anything about you, but like, this isn't cool. Like, this isn't how we learn. You don't cram homework assignments into a WebAssign like that. And they haven't even been assigned, and we have a final on Friday.
Yes.
Like, that just seems like they're trying to like screw us over. That's not cool.
No, we're not. They're not trying to screw you over. This is how it works, man. This is how summer semester works. It moves really fast. And so if you think it's not fair to have assignments due before a final, this is an 8-week course, not a 16-week course. 16-week courses is during the semester, they're more spread out. But during an
Well,
eight-week
it's
course,
not that we have to do the assignments. It's that they haven't even been they're not even available to us yet.
that's what. So I'm looking on WebAssign now. So just like on Canvas, right? There's like an availability for the assignment of when it appears. And actually, I think Canvas is a little different because as soon as we publish an assignment on Canvas, you can see it's where it's published, and then you can see when it's going to be available, right? WebAssign works a little bit differently. So they're scheduled to like make themselves available, but unfortunately you can't see which assignments are available until like they make themselves available. So this has essentially been how it has been all semester. There's only been a handful of assignments that are listed on the current assignments. Like if you look at the current assignments tab, and let me see. So let's pull up WebAssign real quick and take a look, since we want to take a little bit of break and address this WebAssign issue.
It's cool. Let's just keep going. It's fine. We can't do anything about it.
Because this is what you see, right? And if we open Student View, it may not work. Sometimes Student View has been buggy. Yeah.
If you open Student View, we can't see that any assignments. Like I thought last night was the last WebAssign.
You can't see.
Like we don't have any current. Well, we can see the ones we've already done.
Do you guys have like a current, past?
This isn't in this. It's not in our control. Let's just keep going.
There's no future. It's only current and past. That's why
Right.
like it just randomly shows up.
And so this is kind of what's been scheduled all semester. So whenever you have a current assignment assigned, it'll show up. So you haven't been able to tell what type of future assignments you have all semester. Like that hasn't been available. You don't know when the next assignment is going to come up. It is a little bit of a problem with WebAssign because unlike Canvas, in Canvas, as soon as we publish an assignment, you can kind of see when that assignment is going to become available. Whereas on WebAssign, it's not available until it's scheduled availability. And so you just finished 22. We'll open up and extend 22 for you. I'm pretty sure that shouldn't be a problem. And then you'll have 2 more. And yes, they are going to be due the day before the exam. Typical semesters, we don't have exams in the middle of a class day. There's a outside scheduled exam that's 2.5 hours long that is during exam week. It's not the way summer semester works. That's the way the schedule worked by the administration, that they want our last day to be on the very last day of class. And so because we still have material to learn this semester, it's just the way it falls. Like, we still have to finish polar coordinates. And so polar coordinates are going to be finished within these last 2 assignments, the 21st and 22nd. I would imagine that this one, so the 23rd, looks like it'll be available today at noon. Tomorrow at noon, the last assignment will appear on your website. So they will be made available. But just like throughout the entire semester, you haven't ever had an idea of what future assignments have been able to come. So to think that the last homework was the last one was kind of just a misunderstanding of how these assignments have been posted all semester.
That's not the point, but it's fine. Let's just keep going. We're already.
So let's talk about polar coordinates. One person said, I guess to the last point, want to be able to work on these right now so you can focus on studying before the exam. I can open up earlier. That's not a problem. I'm pretty sure we can make that happen as well if you guys want those web assigns open earlier. So let's jump into polar coordinates. We have x, y, normal Cartesian system. Now, we've shown that on a specific curve, we can model those by parameters of time. And we've also seen maybe we want to model it by a parameter of theta. The idea behind polar coordinates is that we can actually model the entire plane with respect to the distance from the origin and a reference angle. So now, rather than restricting ourselves to a specific curve that we might be lying on, we can be anywhere in the XY plane and so typically we have our X and Y coordinates modeled by where those parallel lines or perpendicular lines would hit the x-axis and the y-axis respectively. So now what we want to do is think of it as having some sort of radius from the center. So that's our distance from the center. And some reference angle. So we're going to measure all of our angles, just like we did in the unit circle, way back when you first learned the unit circle. Our theta is measured from the positive x-axis and measured counterclockwise. So we can have both xy coordinates and our theta coordinates. And so how do we actually convert between the two? Well, we just use our basic trick. So maybe we'll draw a bigger picture. And it doesn't matter. Let's actually pick a point that could be in a different quadrant. So of course our theta is that angle. And then we've got our x distance and our y distance. And so the equations we're going to come up with are going to be x is equal to, so I didn't write it, of course the radius is the length or the distance of the point from the origin, is going to be our cosine theta. Y is going to be our sine theta. The other equations we're going to have, of course, we're going to have the Pythagorean theorem, r squared is equal to x squared plus y squared. And then the tricky one is going to be theta. So theta is going to satisfy an equation where we've got to use a trig function. In this picture, it's a little easier to see. If I take tangent of theta, we're going to get y over x. And so that's going to be the case wherever theta is, but we do got to be careful here with this equation. And we want to be careful with which quadrant it's in. Because a lot of times when we solve this, I can't solve this for theta. If I say theta is arctangent of x over y, what's the problem there? Arctangent is restricted between minus pi over 2 to pi over 2. And sometimes, of course, we're going to have points in all of the coordinates in quadrants in all the quadrant 2, 3. And so we need a more general equation. We have to keep it as tangent of theta. And just remember that when you're solving such an equation, you're often going to get solutions in two different coordinates. And so you have to use the given information you know about where x and y are to determine what the appropriate theta is that corresponds to that. So some basic examples. Let's say convert points from Cartesian to polar. This is going to be very much like unit circle stuff you did in pre-calc. So if we have the points, say 2, 2, and this is, usually it's pretty clear. Sometimes, I don't know, I like to put an x and y over it. Sometimes they might indicate that it's Cartesian or whatever. It's usually pretty clear whether the coordinate is x, y, or r theta, because the thetas are going to be unit circle thetas. So pi over 2, pi over 4, 3 pi over 4, things like that. So if this is our Cartesian, how do we solve for our r? Is just square root of x squared plus y squared. And how do we solve for our theta? So tan of theta equals 1. And so, of course, to do it properly, you would remember that theta is either going to be pi over 4 or 3 pi over 4. 5 pi over 4. So either in the first or third quadrant. But since we know our Cartesian, our point is in the first quadrant, our theta is going to be pi over 4. So our r theta coordinates, another way we might indicate it is we just put the coordinate r theta and then say what that's going to be equal to. So we found 2 root 2 and then pi over 4. So any of the other points, let's try to think of another one. Let's use some other coordinates. Let's say -3 and then 3 square root of 3. So how do we convert this? We want to do something similar. So our radius is going to be square root of -3 squared plus 3 square root of 3 squared. And that's going to be square root of 9 plus 9 times 3 is 27. So square root of 36 gives us 6. And then our theta y over x, simplifying, tangent theta equals negative square root of 3. Of course, draw your reference triangles. I always tell all of my students in pre-calc, there's only 2 reference triangles you need to know. 1 root 2, and that's our pi over 4, pi over 490. And then the other one for pi over 6, they're 30, 60, 90. Short side's 1, hypotenuse 2, other side is root 3. So if you see root 3s coming up, you pretty much know we're in this triangle. You just got to figure out which reference angle you need. And we need tangent of theta to be a square root of 3. So the reference angle we need is pi over 3. And then figure out the quadrants. What quadrant are we in? We've got negative x, positive y. So we're in quadrant 2 with a reference angle of pi over 3. That means theta 2 pi over 3.
Could you just draw the unit circle and go from there too?
If you know the unit circle, yeah.
Cool.
My philosophy with math is always try to memorize as little as possible. So of course I memorize these 2 triangles and then you can use those to fill in the unit circle. If you know the unit circle and like to, draw the angles and fill in the values that way, perfectly valid. So our theta is 6 and then 2 pi over 3. Now, one thing to note, is that polar coordinates are not necessarily unique. I don't want to do too many
you go
examples.
back real quick to the, do you mind just like flipping the page around? I just wanted to take a screenshot of it real quick.
Sure. So just like in the unit circle, when we're solving these trig values, I didn't really find all of the values for this equation. Tangent of theta equals 1. Pi over 4 is our initial value between 0 and 2 pi. And of course, we found the other ones and realized it was in the wrong coordinate. But I could add multiples of 2 pi to these values of theta. And if we did, we would still essentially get the same point. Namely, our theta is going to be the same as our theta plus any multiple of 2 pi. Right? In the last one, we had 6, 2 pi over 3. That would be the same as 6, 8 pi over 3. Common practice. Though, is to restrict theta between 0 and 2 pi. But just a heads up, you might see angles that are bigger than that. And you can always reduce, if you want, if you see something like 8 pi over 3 as your theta, you can always bring it back to a 2 pi over 3.
Can you scroll up really quick for a second?
Sorry. So how do we do curves in polar coordinates? This can get a little tricky, and just like parametric equations, it takes some practice. So it's worthwhile to just try to plot all the functions you're given in any problem and try to just at least make sense of why the plot matches the equations. So for example, let's start off with some of the basics. If we have a curve, so usually we have our curves as r as some function of theta. So r is our dependent variable, the radius, and theta, the angle with which we're traversing around the Cartesian plane in our counterclockwise manner, is our independent variable. So if we have things like r is equal to 2, what is this saying? This is saying I am looking for all the points on the plane whose radius, whose distance from the origin is 2. Meaning, so we're going to have the point 2, 0. But now what we want to do, so how we kind of draw these curves, you want to always, I like to start on the positive x-axis and figure out what value we're at. And then you want to think of just rotating around. And sometimes as we're rotating around, that distance can change. And so we're going to rotate around counterclockwise, but what are we changing as we rotate around? We're not changing anything. The distance from the origin is going to remain the same, meaning that we are simply going to have a circle. So my axes aren't the best, my drawing, not the best of circles. But the set of points whose distance from the origin is always 2 is going to be the circle of radius 2. And so we can kind of think of it as theta. As theta increases, as we're going around, the radius is remaining constant. What's going to happen, though, if we change it to something non-constant? Let's get more space. If we have just r equals theta, in rectilinear coordinates, this was kind of like y equals x. Should be an easy function, right? In polar coordinates, it gets a little more complicated. This is saying the radius is equal to the angle with which we're at. Now, the origin, we didn't talk about when we were just doing those points. But whenever the radius is 0, what's that mean? It means we are at the origin. We are a 0 distance from the origin. And if you're a 0 distance from the origin, theta actually doesn't matter. So let's try to graph this real quick. We start at, we're kind of facing in the positive x direction. However, maybe I drew this backwards. Since theta is our independent variable, let's put it here on the left. And let's pick some common values of theta. Since r is equal to that, we're going to have those exact values. I'm going to make it a little hard to draw. Exactly, at least. The shape, overall shape isn't terrible though. So we're starting at the origin, 0, 0. Now as theta is pi over 6, we're going to be pointing along this line, and our radius is going to be pi over 6. So it's going to grow a little bit. As we get to pi over 4, we're along this radius. So this is kind of another way to help graph those. At any given angle, maybe you put dotted lines or draw these rays going out from the origin, and then you want to plot the radius, the distance along that line is going to be the value of r. So our r is going to be pi over 4, so that's going to be a little bit bigger than pi over 6. At pi over 3, the radius is pi over 3. And so again, that's going to be bigger than pi over 4. And so as we rotate around, the radius is going to grow. So here, this value would be pi over 2. Our angle's pi over 2, radius is pi over 2. And so this one is going to form a spiral. So it's going to keep getting bigger and bigger. And even as theta increases, it'll keep going. So a couple of other examples. So just with rectilinear, sometimes we have theta as a function of r. We can switch the independent and dependent variables. You won't see it very often, and most commonly, if you're going to see theta as a dependent variable, you're going to see these constants. So we'll say theta equals -1. Or, sorry, -1's a bad value. We'll say theta is equal to minus pi over 4. We want to pick known angles for theta. What does this mean? So we're restricted on an angle. So if we start from our positive x-axis, negative pi over 4 as an angle is the angle that's pointing in this direction. And this is going to tell us that r can be anything. Radius can be anything. And then careful with negatives. So we kind of just saw that, well, I can add 2 pi to theta and get the same coordinate system in r theta in polar coordinates as we do with rectilinear. And now we actually also have an issue with the radius. Typically, we measure our radius, our distance from the origin, as positive, but theoretically, there is nothing wrong with having a negative radius. So if we just have an equation where theta is restricted to pi over 4, well, if r can be anything and my r is positive, that means we're going to be going in this direction for all positive values of r. But if r is negative, then we're going to be going in the opposite direction. So we can add that if we have r theta or have a negative r theta, this is essentially the same as taking the positive r but rotating the angle by pi. So the last one I want to do, you'll see trig functions come up quite a bit with a lot of these polar equations. Let's do r is equal to 2 cosine theta. So let's graph. And then the other thing let's start working on is finding Cartesian equations. So graphing, this one will be a little harder to graph. I don't think the actual shape is hard, but to understand the process of these, again, just like in parametric curves, really helpful to draw a table. So let's pick some known values of theta. I'm just going to go with my pi over 4s. Usually multiples of pi over 4 is good enough for me to kind of get an idea of the shape of the graph. Let's go up to pi, and then if we need more, we can fill it in. So what's our radius? So r is 2 cosine theta. Let's plug in our values. We will get 2. Cosine of pi over 4 is root 2 over 2. So that'll be root 2. Cosine of pi over 2 is 0. 3 pi over 4 is going to give us negative root 2 over 2. So negative root 2. And then at pi, we will have cosine of pi is negative 2. So this one's going to be a little weird. We've got some of these negative r values showing up. And yet we have kind of nice values of theta. These are all first and second quadrant values of theta. And so let's see how we work with this. So theta is equal to 0. Think of ourselves, our arrow is pointing along the x-axis, and we want to go a distance of 2. So we're pointing along the x-axis, go a distance of 2. At pi over 4, so we'll draw some guidelines here in green. That's our pi over 4 line, pointing in that direction. And we want to go a distance of square root of 2. Now, of course, graphing square root of 2 is kind of hard. Maybe if you remember from calculus, from doing linear approximations, that square root of 2 is approximately 1.5. So it's going to be shorter than this distance. It's actually going to be maybe there. And then now at pi over 2, so theta is pointing upward. But the distance, the radius we're at is 0. So meaning that's going to force us to come all the way back down. So I think I put this plot a little weird. It should be right over our first tick mark, actually. We'll see why when we do the Cartesian, if it's not kind of clear why we should be right over 1 there. And now let's deal with these negative r values. So 3 pi over 4, our line, our angle is pointing in this direction. However, the radius is negative, so we have to go along that line in the opposite direction. And so we're going to a negative root 2, right? So we're facing this direction, but negative means we walk in the opposite. So now we're going to be down here. And then what's going to happen at pi, again, we've kind of got a weird thing where we're facing in this direction. Our angle pi is saying face towards the negative x, but the radius itself is negative, so go in the opposite direction of that arrow. So walk 2 units to the right. So this point brings us back to where we started here. And so this shape actually ends up being a circle. So we started here and we're walking around. And as theta increased, so our theta, remember, just kind of went like this. Our theta is increasing, so our points, if we had filled in more, we would see walking around this circle. So find the Cartesian equations. Let's go ahead and try to figure that out. Cartesian equations, we've got r is equal to 2 cosine of theta. So let's see. Some things we can do. There's different ways of going about it. Let's write down essentially all of these formulas that we use. And then solving these, or at least going from one coordinate system to the other, going from polar specifically to Cartesian is actually a bit harder sometimes because you've got to make substitutions and you have a little bit of freedom in terms of how you want to go about doing this. So what we want to do is potentially look for different options, try to think through what might be the easiest way. One thing we can do, so r, we could take a square root and say r is square root of x squared plus y squared. And then 2 cosine theta, we can then back substitute for x. We could also try to manipulate this equation a little bit, like if we square both sides to come up with a formula for it. You want to be careful with doing that, of course. Squaring both sides of an equation sometimes gives you some extraneous solutions. So let's just keep it as it is and kind of do the official process. Our r, of course, when we take a square root, it's also only giving a positive square root. Let's go ahead and try that. So our r, let's write as square root of x squared plus y squared equals 2 cosine theta. So now the question is, well, how do we deal with this cosine theta? And again, we have a couple of ways. We could try to take arctan of both sides and write theta as arctangent of y over x. Again, we got to be careful of that though, because arctangent does have a restricted domain and range. The other thing you can kind of think of, well, cosine of theta is x over r. And if we are using r, square root of x squared plus y squared, we can convert that r back to rectilinear coordinates the same way we did with the right side. And so nicely enough, if we multiply those square roots over, we get rectilinear equations for it. So that's a Cartesian equation. If you wanted to put it in a more well-known format, and that should be a negative there. Add 1 to both sides, you can completely square. And we see a more nice, well-known equation for a circle of radius 1 whose center is at 1, 0. And so, of course, to kind of go back to our issue of drawing, since we know the angle was pi over 4, and I had a radius of root 2, if that distance is root 2, you can kind of guess that the side lengths are each 1. So it should have been right there above that 1. Any questions on that? Okay, so we've only got a couple minutes left. Let's try to use it effectively. Since our Tuesdays are usually pretty short, I'd like to do more examples with graphing because, again, to get used to it, you kind of just got to graph a lot of these. So practice a lot of these problems from these section. I think it's 9.3. I kind of want to get into the calculus a little bit so that way we're not behind on the calculus, and then during doing the calculus we'll be able to see a lot more of these examples and work out some of these graphs. So tangent lines. If we want to find dy dx, we want to use the same chain rule that we were using with parametric curves. And so since we had y as our sine theta and x is our cosine theta, we just compute those derivatives. So dy d theta, now we've got to be careful though, because r itself, we want to think of as a function of theta. So we've got a product rule here. dy d theta is going to be the derivative of the first term. So that'll give us our dr d theta sine theta plus r times the derivative of sine theta gives us cosine theta. For x, we do something similar. We're going to have dr d theta times cosine theta plus r derivative of cosine is negative sine theta. So we need a minus sign there. So example, we can start with this guy tomorrow. And we'll practice graphing this. Tangent line 2, r is equal to 1 plus sine theta when theta is pi over 3. So we'll practice graphing that again. We see these trigs, these sine and cosine come up. Sine and cosine, of course, they are trig. It all came about from angular and polar identities from the get-go, from this unit circle. So we're going to see a lot of trig functions come up in this section. But now when we perform these operations, these 1 plus sine theta, it throws things off quite a bit. It's not like a linear shift like we would see y in terms of x, right? If I had y as 1 plus sine theta, that's easy, right? It's a sine graph shifted up 1. As soon as I now have the radius is 1 plus sine theta, it gets a little wonky. This is going to be what's called a cardioid. It kind of starts off as a circle, but then it has like a bump in it. It looks like a heart. Okay, so any other questions? You guys feel free to stick around. Happy to talk about stuff. And I will try to get WebAssign open for you guys. Of course, the last one, I do agree. We should extend that for you guys. And then if you want, I'm happy to open up the other ones early if you guys want to get started on those. So that way you can recap, everything else from the course that you want to study on as well.